Okay, in this lesson, we're still talking about summary measures in descriptive statistics. Another important way to discuss our data is in terms of dispersion. Sometimes these are referred to as measures of variability, and really all they discuss is how spread out or how clustered your data points are to one another. How consistent or inconsistent they are is another way to think about it. So measures of dispersion tell us how much confidence you can have that your measure of central tendency is representative of the data. So they're just one part or one facet of an interpretation. So the goal of descriptive statistics, again, is to organize and summarize. Measures of dispersion are summary measures. They provide you one number with the goal of telling you how clustered or how spread out all those data points are. And there are a variety of measures of dispersion, just like there are a variety of measures of central tendency. And so they all have different purposes. So we'll only cover a few of those here. So dispersion matters because it helps us determine whether our measures of central tendency and other statistics for that matter are informative, how confident we are in the results that they're representative. If we're not confident that the measures of central tendency or other statistics that we're using to represent the data are good, then why would we use them to hold them up and say, here's what the real level is in the population? So measures of dispersion allow us an appropriate or allow us a level of confidence. We particularly rely on measures of dispersion when we're making comparisons and looking for relationships between multiple groups or between two variables. So look at the data below. What you see is two groups, A and B. The endpoints are both different. In group A, the endpoint is 50 and 100. In group B, the endpoint is 60 and 85. Both of the groups have a mean and a median equal to 75. So my question to you is, which group do you have more confidence that 75 is better representative of that group? So the scores in distribution A are more spread out than those in distribution B. Because their spread is different or because their clustering is different, they have different dispersion or variation. And so typically we're more confident about our summary measures of central tendency, like the mean and the median, when the points are clustered together more tightly and less spread out. So for purposes of this comparison, we're more confident in group B that the mean and the median are best representative of that group compared to group A. Mathematically, the median and the mean are the same, but because of the spread, because it's greater in the first group, we just have a little less confidence that it's representative of all the points. So measures of dispersion and variation represent that clustering or spread in the data. The purpose is to provide us a number that gives us a picture. So again, it provides us that one value that tells us how spread out or how clustered the data points are. Measures of dispersion or measures of variability, I interchange those two terms, typically give us a number in terms of distance so that we can figure out how far away points are. The further away points are, the more spread out they are. The smaller the distance is, the more clustered they are together and the more representative they are of the data, or the more consistently they are in agreement with one another. We refer to this in terms of homogeneity and heterogeneity. When data is clustered together more tightly, it's more homogeneous. When data points are spread more apart and spread out further than in some other group, they're more heterogeneous. And so a dispersion measure of score of 0 indicates that you have a perfectly homogeneous data set, meaning all the data points are the exact same. Everything is exactly consistent. But when you have large distances or large measures of dispersion, the score means that the cases are dissimilar or much more inconsistent or much more diversity in the data points. So there are different dispersion statistics. We'll talk about 2 or 3 of those here relatively quickly. The first is the range. Then we'll talk about the most commonly used, which is variance and standard deviation, and the two are directly related to one another. The range is the most simple measure of dispersion to calculate because you're using data that exists at the interval or ratio level, and so you take simply the two endpoints, the highest value and the lowest value, and you subtract one from the other. And what you get is the distance from the most basic point in the data to the highest point in the data. And so if you have a large number, you have a large distance from one end of the data to the other. If you have a small number, it means your data points from one end to the other are more compact. That's the idea. So it uses the extremes of the distribution to figure out the scores. So in this instance, our data points are ordered from least to greatest, so we can easily pick out the smallest and the greatest value. 215 and 95, so we subtract 95 from 215, we get 120. So thus the range for the data is 120. That's the range value. That's the distance from one end to the other. So the larger the number, the greater the distance. In terms of calling this a homogeneous data or heterogeneous data, it's all relative compared to what your points are referring to. So if you're comparing it to another group of similar data, then you can say it's more homogeneous or more heterogeneous. But just to say that this is heterogeneous or homogeneous based on the range, it's difficult to assess. You need a real comparison. So in the original two groups, back to Group A and Group B, the range for Group A would be 50 points, 100 minus 50. And the range for Group B would be 85 minus 60. So that's 25. So clearly Group B is much more homogeneous than Group A, or vice versa. Group A is much more heterogeneous than Group B. Because when you compare the ranges, you have a smaller distance for Group B than for Group A. Of course, there is a problem with the range. It only uses two scores to calculate the distance. It uses, as a point in fact, the two least representative points in the data, which is the extremes, the minimum and the maximum. The minimum and the maximum are usually unlikely to represent the vast majority of the rest of the scores in the data. So that means it gives us a bad picture of the data distribution, or some would call it a crude picture of the data distribution, because it's not very sophisticated, because it only uses those two least representative points. So look at the two data sets at the bottom here. So if you look at all the scores, every score is the same except for the last one. They have the exact same numbers of scores, and the endpoints are different. Distribution on the top, the last score is 7. The distribution on the bottom, the last score is 100. The two distributions are pretty much the exact same except for that one particular point. So if you find the range for the top group, you're looking at 6. If you find the range for the bottom group, you're looking at a range of 99. So 6 versus 99, it's quite clear that one group is more heterogeneous and one is more homogeneous than the other. But if you look at all the scores in the data and consider every score in the data, they're pretty much similar to one another except for that one little itty-bitty score. And so the problem with the range is it takes the least representative scores and gives you a distance. It doesn't take into consideration every value in the data distribution. So the idea here is that we're dealing with distance. So instead of using extremes, a better approach to assessing how much dispersion or variance there is in the data is to figure out the distance between each score and then find the average distance that there is in the data so that we can find the total amount of dispersion and figure out what the average amount of dispersion is. So typically we find distance among scores by subtracting each individual score from the mean. So this automatically assumes that you're using interval and ratio level data. So if you're trying to find an average distance between points, you've got to be using interval and ratio level data. So this gives you a distance away from the mean. So if you find every score's distance from the mean, that's called a deviation score. Then our goal would be to try to average the deviation scores such that Lower averages mean the data is more homogeneous. Higher averages mean the data is more heterogeneous. So we can find an average distance from the mean. So for instance, with these data listed here, we would have a mean of 6. If you add 3, 4, 5, 6, 7, 8, 9 together, you get 42. Divide by the number of points there are, which is 7, you get a mean of 6. So we take 6 minus 3, 6 minus 4, 6 minus 5, 6 minus 6, 6 minus 7, 6 minus 8, 6 minus 9. So each one of those is a deviation score. So we get a deviation score of 3, 2, 1, 0, negative 1, negative 2, and negative 3. So if we wanted to find the average deviation score to figure out how heterogeneous or how homogeneous our data points are, we can just add them all up and divide by the number of deviation scores that there are. The issue is if you add all the scores up, you're going to get a result of 0. So one method of resolving this problem is to remove the negative signs of the distances before we add them, right? Because you have, remember, think of the mean as the balance point. The distances above the mean equal the distances below the mean. So if you add all the distances below the mean, which are all going to be negative values, to all the distances above the mean, which are going to be positive values, you'll always get 0. And then anything, when you get 0 divided by whatever number, you're always going to have 0. So it's difficult to find the average distance or the average deviation to determine how much heterogeneity or homogeneity there is in the data. So the initial problem here is the signs, those pesky negative signs. So there are ways to get rid of negative signs. So one way of getting rid of negative signs is using the absolute value. Right? Remember, sometimes from your algebra class, this is called putting railroad tracks around the number. So the sum, if you took the absolute value of every single number here and you added them all up, you would get a sum of 12, and then you could average it if you preferred. But just using totals, it's kind of unfair, because if you have more data points, you're going to have greater distances, typically. What we're looking at here is a formula. We're looking for D as a measure of dispersion. So this capital sigma, this funny looking E, is sigma, which is a mathematical command to sum everything together. So you're summing the absolute value of every score minus the mean. If you add up all of the absolute values of the deviation scores, you'll get this dispersion value. So the idea behind the D score is simplistic and easy to understand. Right? Higher numbers would indicate more heterogeneity, lower numbers would indicate more homogeneity. However, if you have more scores in your data, you're going to have inherently more heterogeneity. And so just because you have more scores doesn't necessarily mean you're more heterogeneous. So here's an example of that. In group A, we have 4 scores, but we have a deviation score of 22.5. In group B, we have many more scores, but the deviation score is very close to 24. But if you look at the deviation score, or if you look at the scores in group B, it's clear that they're much more clustered together tightly than the scores in group A. But this distance or the deviation measure we've provided here doesn't do that comparison justice. So we would need to find an average. So you could take the total, 22.5, and divide by 4, or you could take that 24 and divide by the number of scores that there are, and you would get an average distance. And that's what this slide is telling you. So when you divide 22.5 by 4, you'll get 5.625, and when you divide the distribution B, which is the sum of 24 divided by 25 scores, you get a deviation score, or an average deviation of 0.96, right? So when you compare 0.96 to 5.625, right, it's clear that group A has a much more heterogeneous data than group B, which has a much smaller 0.96 value. So the results are expected since A is indeed more dispersed than B. So now you're finding the average, whereas the top part of the formula, right, the sigma score minus the mean, the absolute value, then you're dividing by the number of deviation scores that there were. So now you're finding the absolute deviation. The issue with absolute numbers is once you transform a number, we'd like to be able to undo that, because technically we're dealing with the absolute values of the deviation scores, not the deviation scores themselves. So ideally, we want to undo that, but we can't. You can't undo an absolute number. So we must find another method of resolving this plus minus issue where we get the total of 0 when we add up all the original deviation scores. So another way of getting rid of negative signs is to square a value. Once you times something by itself, no matter if it's positive or negative, the result is a positive number. So this yields the same result. So you're going to square each deviation score as opposed to just take the absolute value of it. So if you square it, you get rid of those negative signs, then you can add up all the scores together, and you'll come up with some number. Ideally or symbolically, higher scores typically would mean more heterogeneity, lower scores would mean more homogeneity, and then you can find the average, so that when you're trying to compare groups with different numbers, you come up with some comparable term that takes into consideration how many scores there are. But in this instance, we're dealing with squared deviation scores, not original deviation scores. This is called variance. So if you look at this formula at the top, we take this x minus the x bar, which is the mean. We square it, and then we add up all those squared deviations, and then we divide by the number of deviations that there are. This is called variance. And this is a common measure of dispersion. But variance has the same problem that the absolute deviation had. And that's, you're still dealing in unoriginal terms. So with the absolute scores, we had to take the absolute value. Here we're dealing with squared scores, which doesn't really help us much. So because we're dealing with squared units, we can somewhat undo what we did by taking the square root. So if we take the square root of that value, so the final adjustment here is to undo what we did. So we squared everything. Now we're going to take the square root of our result, and that should theoretically, but not exactly, put it back into original terms. So this is why we prefer squaring to get rid of the negative signs as opposed to taking the absolute value, because once we square something, we can take the square root of it and get back into a more traditional scale of measurement, the actual scale of measurement that we were using to find the deviation scores to begin with. So when you're looking at SPSS output, it'll just give you the standard deviation. And in this case, notice that we have the column headings, N for number, the number of scores that there are, range, it'll give you the range, it'll give you the mean, it'll give you the standard deviation, it gives you the variance. And if you look at the standard deviation for each variable listed here, and there's 1, 2, 3, 4, 5, 6 variables listed here, if you take the standard deviation and square it, you'll end up with the exact same variance that you see there, side by side. So the standard deviation suggests that the typical distance away from the mean. So let's look at the first variable, seriousness of crime estimates. For the mean for that variable is 101.62. What that means is, or how you interpret that is, for the standard deviation, the average distance that any score is away from the mean is roughly 20 points, where the mean is 101.62. When you look at significant others worry about victimization, the mean is 31.3710, but the standard deviation here is 15 points. So that means the typical distance that any score is from the mean is 15 points, either 15 points above or 15 points below. So if you're trying to figure out what a typical score is, you take 31.371 plus 15.5, and that gets you a high end. And if you're trying to figure out what a typical score is on the low end, you take 31.371 minus 15.5, so that you have a range. So somewhere, just ballparking it just by eyeballing it, not using a calculator, I see that my range is going to be somewhere around 15 to 46. So that's a 1 standard deviation range. of what a typical score is here. So if we really wanted to compare variables, we could take their standard deviations and divide them by each one's mean. So you take the standard deviation for worry about being a victim of crime, and the standard deviation is 2.27, and you divide it by 3.75, and you get a value of 0.606. And when you look at the second variable, or another variable, personal interaction learning, the standard deviation is 41.67, divided by the mean 165.92, and you see that this value is 0.25. So because the two variables are measured differently, this is an attempt to compare how heterogeneous and how homogeneous one variable is over the other. And it looks like in this case, personal interaction is more homogeneous because of this 0.251 is smaller than 0.606. So even though the original standard deviation was larger, being larger is relative to where the mean is at. So when you're measuring variability, it's mostly a concern for interval and ratio level data because it requires you to find a deviation from the mean, and you can only really use the mean when you're dealing with interval and ratio level data. There are measures of dispersion for ordinal and nominal level variables that we won't discuss here, but the idea is the same. You're trying to establish heterogeneity and homogeneity, and the more heterogeneous your data is, the less confidence you have in the values that represent it. So we use numbers to provide a single value to describe the dispersion. So when you're dealing with interval and ratio level data, the preferred method to describe dispersion is the standard deviation. And we can use box plots to help us figure out how spread out or how clustered together our data is. So if you recall from the last lesson, we plotted dispersion, those boxes and whiskers for different groups, and notice that when the box was small and the whiskers were small, we said that the points were more consistent and clustered together. And when the boxes were longer and the whiskers were longer, we said the points are much more inconsistent and they're more spread out. So a box plot is a good visual representation of how clustered or spread apart your data points are.